She's one of our most popular alumni, and we are very happy to have him as one of our last guest lectures in our course. This is a series of different lectures. You can find them on YouTube. And today I will have this talk called From AlphaGo to AlphaStar and Beyond, a journey in reinforcement learning. In case you know Oriol, I will read his bio. So Oriol Vinyals is a principal scientist at Google DeepMind and a team lead of the deep learning group. His work focuses on deep learning and artificial intelligence. And prior to joining DeepMind, Oriol was part of the Google Brain team. He holds a Ph.D. in EECS from the University of California, Berkeley, and is recipient of the 2016 MIT TR35 Innovator Award. His research has been featured multiple times at the New York Times, Financial Times, Wired, BBC, and many other media. His articles have been cited over 90,000 times. Some of his contributions, such as sec-to-sec, knowledge distillation, or TensorFlow, are used in Google Translate, text-to-speech, and speech recognition, serving billions of queries every day. And he was the lead researcher at the AlphaStar project, creating an agent that defeated a top professional at the game of StarCraft, achieving Grandmaster level, and also featured at the cover of Nature. At DeepMind, he continues working on his areas of interest, which include artificial intelligence, with particular emphasis on machine learning, deep learning, and reinforcement learning. So Oriol, thank you very much for being with us today. If you just allow me, just very small disclaimer for our students. So you know that students that this talk is being streamed publicly. So if you turn on your camera on your microphone, you might go public, and that's going to be recorded. If you want to interact with Oriol, which I think you are welcome to do it, you can do it with the camera's microphone. Or if you want to keep it private, just use the chat and I'll read your questions. Okay? So Oriol, the screen is yours. Thank you very much.
Great, thanks, Xavi. It's really my pleasure to be here. It's always very special to be coming back to your alma mater. Although I'm really not there physically. I'm in London right now, but the year is 2020. I guess we've had some challenges, but I'm still super happy to be able to be giving this lecture. As Xavi said, it would be great to have it be interactive, as hard as it is online. I have kind of given this talk in a slightly different shape, more as a talk. But since today we have more of a lecture, I will try to pause and ask for people to ask questions as much as I can. I'll share my slides right now. But yeah, please use the raise hand method, or just in the chat, and then hopefully someone can read it out loud. I won't be able to see the questions though as you type them, but of course if you talk, I'll be able to listen or hear you, right? So hopefully we find a way. Great. So I'm sharing my slides. Hopefully they load properly. If not, shout. And yeah, I thought today I was going to give a fairly technical lecture on a few topics that relate to actually model-based reinforcement learning in particular, but obviously it's also a bit about generically reinforcement learning and deep learning. And it is not that the journey word here actually has a meaning, because this has been a personal journey for me, having joined DeepMind at the time that AlphaGo was released, and then being part of AlphaStar and some of the newer things and research topics we are investigating. So this is actually a journey, like temporarily speaking, which hopefully will make it more close to what also the experience of being a researcher in industry might look like from an individual point of view. And also, I believe, besides asking questions throughout, I would really, I will appreciate any sort of maybe related questions to the journey part, maybe towards the end, where we can have a more informal discussion with, especially those who are tuning in the actual talk with the Google Meetings version. So I'm really looking forward to that discussion as well. Great. So I was saying, year is 2020. It's been definitely an out of distribution experience for the whole planet, really. And I just want to first give a message of perhaps hope that with vaccines and some events turning a bit better, hopefully the gradients are a bit looking more positive so that we can recover, and maybe next year at this time we can have this lecture actually be in person. But obviously things have been quite challenging, and for all of us, including myself, there's days where it gets really hard to do research. So it's very important to use your network and support that you can reach out to for help. I'm always very happy, obviously, to be trying to help people out in any form or shape. Obviously, there's a bandwidth limitation, but you know, feel free to reach out to those of you who have a good network, or your closest friends and so on. It is quite important to realize the challenges we've gone through as a planet, actually. Great. Okay, so let's actually start the talk. I will go through the more basic elements that will be concerning the talk, because almost every machine learning method nowadays, you can sort of analyze it through a few different components. I'm starting with supervised learning, which obviously is not the object of the class, but I think it's useful to realize that even in reinforcement learning, the 4 components that I describe here are essentially the same. So the components obviously involve a few things that interconnect. The first of which, in supervised learning especially, is data. That is the amount, like essentially the input and output that you desire to map to and from in a classical supervised learning scenario. Then there's the actual model. That is where we sort of go all out and try to define the best deep learning / architecture that we can get our hands on to make sure that we have inductive biases, etc., that map the input to the output data. There is obviously then a loss that must be defined, a loss that can incorporate not only the fact that we want this function to approximate the real data, but also other regularization terms, etc., that might be important for the optimization to work well, for generalization to be achieved, etc. And last but not least, optimization, which is sort of the engine that runs through the loss, optimizing the parameters of the model on the data. And these are 4 components that hopefully anytime you're presented with a new problem or even a new field or subfield in machine learning, you usually are able to identify it quite clearly. And obviously, I'm not gonna go more into this, but if you are just interested in this idea or notions in general, there are quite a few references and tutorials online about supervised learning. Now, in this class, I hope you have seen these at length, but it is good to realize why is reinforcement learning actually in a way the same as supervised learning. So in reinforcement learning, we have a slightly, especially the data comes from not a closed data set of input outputs, but rather the data is provided by an engine, if you will, an environment that generates observations from which then an agent must take an action that is then fed back to this engine, and then this engine sort of takes a step and generates a new observation. So the data source here is not a data set, but rather, you know, a game or like a robot that is out in the real world gathering these observations, etc., etc. There is a very important element in reinforcement learning, which I'll discuss later, because it was quite critical to make even the first version of AlphaGo work, which is that of supervised learning, or as it's called in reinforcement learning, imitation learning, which is besides the environment itself, you might get access to actually trajectories of state to actions, which would be the input-output similar to supervised learning over time. And this I put in parentheses because that's not always, strictly speaking, necessary, but this can help quite a bit to get going in solving some of the hardest environments that we can get our hands on. Now, the model, again, this is actually the same as I said before. It's generally a neural network that integrates all the states that the agent has seen so far and produces a distribution over actions. And then the losses, there are quite a few variants and details that do matter. Many papers and research is being done on the loss in reinforcement learning, also in supervised learning, but I would say that the kinds of losses there have converged a bit more. But there's maybe two main families of losses that hopefully you've been told during the lectures. These are the lectures that I use myself when I got into reinforcement learning from Dave, who is a colleague of mine at DeepMind. But there's essentially what's called Q-learning, which is actually what made DeepMind quite famous with this deep Q-learning algorithm. And the idea there is to just build a Q function that predicts the total return of an episode, and it basically tries to learn a neural network that can compute that quantity from any state and given any action that you might take from that state. And then there is the other one, which generally we can call it actor critic, policy gradient, etc., which uses directly the policy instead of just trying to compute the return. It actually uses the policy in the loss explicitly, but also must, and generally it works better if you do also have a value or a Q function aiding or guiding or reducing variance of this loss. Again, I'm not gonna go a lot more into detail on this, just knowing that these are just methodologies of losses that have been quite successful. There are pros and cons of both modes. Interestingly, I generally have a bias for the second set of approaches just because it maps quite much more closely to sequence modeling, which has been maybe the overreaching career path that I've taken from even before starting to do reinforcement learning. But obviously Q-learning is very popular and very important as a technique. And as we've seen, both modes of training and with many more details has yielded a wide variety of tasks that as an environment were able to be unlocked thanks to using more powerful methods, scaling up training, etc., which you might have seen. And in this talk in particular, we'll kind of go through this, as I said, journey from almost a personal standpoint that from which I first learned about some techniques in AlphaGo. Then I'll describe briefly some key components in AlphaStar that actually contrast quite a lot with AlphaZero especially. And then kind of looping back a technique that we're developing that's kind of cutting edge research in the sense that it hasn't even been published, that tries to extend AlphaGo. So probably now it's a good point if you have any questions or comments or feelings about reinforcement learning. I'll start getting a bit into model-based reinforcement learning and then starting to talk about AlphaGo. But if you have questions, I guess chat or raising your hands is a good thing to do, and then we can moderate those questions as they happen. But please feel free to ask a question. I'll sip some of my tea in the meanwhile and continue after that. All right. So I also know that you've been, there was a lecture actually specifically on model-based RL. So let me actually, since there haven't been questions on basics of RL, let's see if someone wants to, even in the chat, tell me what, in your view or from the lecture that you've had specifically on model-based reinforcement learning, in one sentence, how would you describe model-based reinforcement learning? So anyone wants to take a stab at it, you can write it down, as I said, or maybe tell me, like now, I guess, just unmute yourself and say, what do you see as reinforcement or model-based reinforcement learning, rather? Let's see if someone, I'm going to see the chat. No one in the chat. All right. I'll give you 15 seconds, okay? Otherwise, we can reflect on RL so far. And I see Victor is in the call, so I know you know a lot about this, so maybe you can say something. Sorry, you're in my, I switched to my camera and I see your face.
Actually, there's also Ignacio Clavera. I'm not sure he's available, but he was the teacher actually.
Okay, maybe he can tell us what he said. Ignacio, can you say that, please? Do you agree with this slide, or yeah, like how do you describe model-based RL in like 1 or 2 sentences?
I guess the gist of model-based RL is like to exploit more information of the environment to learn a model of it. So essentially use supervised learning to learn a model and then exploit this model to learn a policy with fewer samples from the real world.
Okay, I like it. All right. I think we agree, and probably not randomly, because I took this slide from Chelsea, who teaches and who studied at Berkeley as well. But I like this slide. I don't think there's everyone in the field would agree what model-based RL means. So that's why I paused and I asked, because it's actually it's one of these things that, like meta learning, maybe that not everyone agrees in kind of a standard definition, perhaps. But the idea of model-based RL, maybe the gist of the idea is indeed to explicitly create a model of the transitions in the environment. That's how Chelsea sees it. I agree with that. So if anywhere in your, probably not data, it's a bit hard, but anywhere in your model, in your loss, or even in the optimization, you use an object that might look like this, which is from a state action pair, try to predict what the next state is going to look like, then I would say you're entering model-based RL territory. And then indeed this kind of transition from like, oh, if I take this action and I see this, I'm in this state in the chessboard and I take an action, what's going to happen next? If you have this learned explicitly through a model that could be obviously a very simple model, a lookup table even, or a fancy deep neural network, if you have these, I think you're in the model-based RL territory. How to use this model is where, again, a vast variety of techniques and methods have been and are being researched at the present, and one of which I'll go now in detail, is using search and planning as it was done in AlphaGo. But there really are quite a few ways to use this model, which, again, as Ignacio said, you probably in a maybe a parallel step, or jointly, you will learn with supervised learning, trying to approximate, given the true environments transitions, what this model should trying to be doing. Now, also, I think it's kind of important. I've been somewhat exposed to both model-based and model-free, and I try to distill a bit of like high level, what are like pros and cons, and I think it's not the community is divided. I think it's still not clear which of the two is the way to go in reinforcement learning, and probably it actually depends on the environment, which makes a lot of sense. But maybe let me start with model-based, because one other thing that Ignacio said is very important, which is in model-based, one of the motivations is that if I learn a model of the environment, I will probably be able to learn to act on this environment a bit faster with less data. So I gain sample efficiency. Maybe I am able to transfer to a different reward on the same environment. Like, let's say if you change the rules of the game of chess for some reason, if you have a model, you might be able to learn on this new set of rules much faster. So the idea of transfer is also very important. And last but not least, generality, which means in any unexpected state that you might encounter, akin to maybe out of distribution, model-based maybe has a slightly higher chance to succeed, because it can use the model, which is yet another way to see the same state with a different neural network that might help. There are papers on this last point that point out that if you are in a state you've never seen, both model-based and model-free suffer equally. But I think intuitively, at least, it's an appealing property of model-based. As I said, in model-based, most methods explicitly, but some implicitly, like in mu0, which is coming in the last part of this lecture, will explain, predict future states. and then they use some sort of process or procedure in most cases to, given the model, to search and improve the proposed action that without the model they got through maybe a policy that just looked at the state, proposed an action, but then you use the model further and then back propagate or use some technique to try to improve that action that you picked without the model. Now, another motivation which comes from one of the authors of the main book, perhaps, of reinforcement learning, is a wonderfully written book, I would say. It's obviously probably outdated, although there might be a new edition coming up. But Rich Sutton wrote this essay a couple of years ago, maybe. 2020 is a year that is a kind of a, I don't know if it's been 2 years or 1 year or 3 years, but hopefully something like 2 years ago, Rich Sutton wrote The Bitter Lesson. And kind of the TLDR of that was that the two methods that seem to scale arbitrarily in this way, and in this way meaning in being better at the task given, are search and learning. Learning, it's hard to disagree with. Machine learning is kind of, or learning techniques in general are generally outperforming all the handcrafted feature extraction that we were doing a few years ago, and they're still important in some cases, but learning really scales really well, as we've seen in many examples recently. And then search, which is a form of model-based, also scales arbitrarily. And we'll unpack this claim a little bit later, but I don't think it's as simple as they both are created equal, let's say. And then there are quite a few examples of model-based. Obviously, the one that I learned model-based from was actually from, I believe it was Peter Abil's Ph.D. thesis, where he was using a model to make an helicopter fly upside down. The videos are amusing, so I recommend you take a look at that. And then in robotics, there's world models, poker, obviously AlphaGo and mu0 are all instances of model-based reinforcement learning. Now, model-free is a contrasting to these points more or less, except that there are some caveats, I would say. But the main property of model-free is that there's no future state or reward predicted. We can agree with that. And as a result, generally in model-free, most policies have these, what I call reactive policies, that given what happens right now, they just output an action given some constant time budget. Although there's a caveat there, because even though these neural networks that generally drive the most complex environment policies are constant time, they generally tend to be very deep models. So we can start thinking that maybe the depth of the neural network is a form of planning implicitly, of course. And I kind of buy this intuition is probably correct, that it's not that they're reactive and they don't use thinking time. It might be that if we over budget the thinking time by adding, let's say, 200 layers, and then when the state doesn't require lots of planning, maybe the neural network acts out almost as an identity. But when we are in a situation where a human would think carefully about the next move, then maybe all the layers are doing a bit of planning implicitly, right? So even model-free, I would say there's a bit of planning possibly, and it would be great actually to have results investigating these in some of these domains we work on that clearly are very well suited for planning, such as Go or chess. I heard there might be a question, so it's a good time to ask it if there is a question. But
yes, hi, Oriol.
Hi.
Just one question. When you say model-based, I see that obviously there's poker, there's AlphaGo, and there's games that maybe not easy but straightforward to know the model. But then there's the Stanford helicopter, maybe. How do you? Is it physics, the model that we are basing?
Yeah, that's a very good question. So there's a field that sometimes gets confounded with model-based RL, which is that of control, continuous control in this case. So in many applications, especially before the machine learning kind of took over naming-wise many other areas, continuous control is a form of obviously using a model where you know the physics and the dynamics of the system, which I believe is what the Stanford helicopter was using at the time. So it's more of a control than actually machine learning. But you're right that part of the issue in model-based, and I'll get to that later, is that these environments are fairly trivial to models their transitions sometimes. So I think that's really the challenge, and where the frontier of research is can we model the world? Is modeling the world as hard as solving the task we care about, in which case you might as well go model-free. But it's a great point. Thank you. And I think if you can mute, after asking the questions, try to mute yourself. I was hearing a bit of echo, but hopefully that's fine now. Great. So in model-free, again, some other notable examples. Atari, especially from DQ1, was model-free, although people have used Atari as a domain to test model-based approaches. AlphaStar, robotics appears in both. There are versions or papers that use both. Maybe I should have written Atari on the right side as well. And then maybe the most complex video games to date that we've attempted to do with reinforcement learning, namely Dota 2, Capture the Flag, or StarCraft, they actually all fall into model-free, which is an interesting sort of reflection and might indicate a bit of the challenges of scalability in model-based, perhaps. So I'll try to kind of categorize a bit the things that we'll be talking about during the rest of the lecture. And so to try to maybe distinguish the kind of main properties of each of the methods, I drew this table. I'm not sure it's going to be terribly useful, but let me just quickly explain what the table will contain, right? So here we have methods such as model-free, model predictive control, which is a form of model-based, or world models, which is another form of model-based. I'll tell you how inference works. That means as you train the policy, once you have the policy, do you have to do something special to compute an action? And then whether they use a model or not, and a bit how they use the model, what the loss for training the agent is, and then last but not least, whether this is in principle applicable to any environment that we can get our hands on. As you see from the first three, these are in principle not making any huge assumptions over the environment. So any environment you can train these models, you can apply it. You'll see later on that's not the case for methods such as AlphaGo/MCTS. Now in model-free, this is feed-forward. It doesn't use a model. In model predictive control, I chose this one because that's the one that uses a model of a transition and then uses backpropagation to find the best action to yield a certain next step transition that you wish to obtain. And as a result, it uses a model, especially of the transition, but also it can use a model for future value from the root state that you start doing the search over. And then this one, world models, it's an interesting paper from David Hahn, Schmidt-Huber, actually, that does something slightly different. So that's why I listed it here. The policy actually is feed-forward in principle. It's just a normal neural network, receives the state, produces the action. But it actually uses the model mostly to train as in the loss and in the data, in fact. So the way it works is you train a model, a transition model, and then instead of using Atari, the engine, let's say, to generate lots of experience, you use the model instead to replace the real data with kind of fake data or data generated by your model that is synthetic. And you can generate much more data with that without counting it as an experience that you need to count against the budget of your model. And then you train your standard like policy gradient / Q-learning on this synthetic data that your model generates, right? So this is a bit of generative modeling as a world model, which is quite an interesting connection to generative models, which I believe you've seen as well a little bit, if not in these lectures, obviously during your career. So let's dive into one method that's really how I got introduced to DeepMind. It was a nice way to join a company which was striving with reinforcement learning And 3 months after joining the offices in London, actually, I was going to the office at 5 a.m. because that was when the Korea matches against Lee Sedol were happening, which was a great moment for the company, and I'm very glad I got to experience it really like firsthand in the office. So to give a bit of context, in case you forgot or you might not know the story, there was, chess is kind of a, someone mentioned like it's easy to have a perfect model of chess. It's a fairly simple environment, very discrete, no uncertainty, and we'll get back to these kind of simple environments later. But chess, as you recall, was sort of quote unquote solved with computer programs, thanks to mostly compute power and the ability to also create a value function that was able to identify whether a player was ahead or not based on the value of the pieces that you have in the board. Obviously, that does not always work, but by and large, IBM had one of its breakthroughs with Deep Blue that was doing essentially a search methodology mostly to solve chess. So it actually was a form of model-based, of course, because search ultimately uses a model or the true environment to find a better action given the current situation. Now, what happened, and this was really unlocked by the power of neural networks, was that the game of Go, which has a much higher branching factor and much higher or larger depth, was thought to be impossible to crack with brute force search, which is not really what the chess engine was doing, not through brute force, but clearly the number of possibilities in Go was maybe an order of magnitude larger than in chess. So it really felt like the same techniques could not possibly be applied, that of search. And at the same time, it is very hard to evaluate in the game of Go who is winning, because there's much more symmetry in the there's no pieces that are alive in the board that would tell you the value for each player. The positions, the shape of where the pieces are is what matters, and it's very hard to program actually a value function for the game of Go. Obviously, it's also good to work on a domain that is known to be very difficult and very interesting for humans. Many people love the play of the game of Go. I personally don't play, although I learned from Go. I had a roommate that used to love the game of Go, so I knew about it before AlphaGo. But many people discover the game through the breakthrough, which is obviously fine. But it's very important as you work on research challenges longer term to identify ideally problems that we care about solving, we find interesting. That's why sometimes it's useful to get an external benchmark that you were not able to modify to kind of adapt it to your own algorithmic biases in terms of what you're trying to prove in your research paper. So Go, in that sense, was also a great domain for AI research at the time. And surprisingly, or not surprisingly, what ended up working really well was almost kind of the simplest approach in hindsight, of course, that you could imagine doing, which is that of training two different neural networks that were doing essentially the job that is precisely required to do search or tree search that you might want to do in a kind of search engine that tries to search for the best moves in these kind of games that they're fairly simple in terms of transition, but fairly hard to master. The first component is the policy network. That is exactly the same policy network you've been learning about in the class. And it simply maps the state, which in this case is an image of 19 by 19. There's three values, free and the two colors that are the pixel values of this image. And the policy network goal is to produce a distribution over actions, namely where do you place the next stone at. And this is it, right? That's the policy, and how you train this policy is a question, but in terms of the function that I was saying, that's what the function is doing, right? Is mapping the board state to the move that is most likely to happen next. Now, second step is, as I said, it's very hard to know who's winning. So the value network, which also is a main or a key ingredient in reinforcement learning, is trying to predict, given a board of Go, again, the same kind of input in this case, predict between -1 or 1. That's the exact method that was used for AlphaGo, but you could also predict kind of a multinomial over win, tie, or lose, but between -1 and 1, it's okay as well in terms of mapping these 3 states to 3, -1, 0, and 1 values. But then you're just, again, using a powerful learning method to try to identify which player is ahead and is likely to win this particular board position, right? So these two things, these two elements have to be trained, of course. And interestingly and inspirationally, I would say, for AlphaStar, which I'll describe after AlphaGo, is that in the very first version of AlphaGo, supervised learning or imitation learning was heavily used in the following way. So there is actually a large data set of human expert positions, right? So that's not the environment, but rather this imitation set that in reinforcement learning we can get from the data side. So there actually are a lot of games that were played and recorded throughout history. And the first step of AlphaGo, the original one, was to simply take the board positions and where the player would play, in this case, this red point here, and treat these as a supervised learning task. So from the input, your goal is to classify which output was picked by the human who was hopefully trying to win, who is good at the game of Go. And that is kind of how you pre-train or train the policy network, really. Now, this policy network actually can play the game of Go, okay? It's not great at it. It definitely would beat me, probably, but it has sort of a reasonable idea or where to put stones given what it's seeing so far in the game. Now, you can take this policy network and then run it as if it was the policy that you're trying to create in AlphaGo. You run this policy, and then at the end of the day, you run this policy against yourself, right? So you start adding self-play here, and then you record who won this game. Was it like black or white, right? And then once you record who won the game, which is this reinforcement learning arrow, you then use the actual value achieved by your policy to then train a value network, right? So you're first training the policy, imitating humans, and then in the second step, you're training a value that tries to predict who wins given your policy, right? So you want to be on policy, if you remember the lectures. So that's what AlphaGo version 1 did, which actually is a bit complicated. You need the supervised learning, and we'll see in a second that this was largely improved later. But in gist, that's how it worked and how you train both P and V. More importantly, is like once you train these policy and value networks, how are you going to use them to create a superhuman Go player? And this is where sort of the retrospectively obvious the algorithm appears. But I think this is one of the most elegant, I would say, novel ideas to combine classic sort of AI, which is search, with the learning paradigm that we're seeing in machine learning. And this kind of result is also what motivated Rich Sutton to probably write about what I discussed, which is this bitter lesson where learning and search both scale. So to use these two components in search, it's actually fairly straightforward. In search or in tree search, we have two main limitations. One is the branching factor, and the other is the depth. And the more we want to exhaust the tree of possibilities, the more we have to consider all the possible branches and going all the way to the leaf node of, oh, the game is over, tell me who won. The policy network is able to discard some insane looking moves that you wouldn't want to expand in your tree search, right? So you can prune the tree search by eliminating obviously wrong choices, and your policy network can guide you through that by saying, hey, humans are not very likely to play 99% of the moves given this board. So please just focus the search over the area of the tree that humans are likely to play, which means that the good games are likely to happen. So first element, very important, the policy is reducing the breadth. And the second, which is the depth, is where value network enters, right? So you don't want to possibly run the game always to the end to decide whether, you know, this branch looks good or not based on all the possibilities that this branch yields in terms of min-max games, which are these kinds of games. So what you're gonna do is you're gonna truncate the search, and at some point rely on the value network, which hopefully is better than at the root, because now the board is more finished. So the closer you are to completing the game, the better hopefully your value net is at predicting the winner. So you're trading off depth for accuracy, but you're relying a lot on your value network, which hopefully is so good at identifying who is ahead in the game of Go. In the game of chess, this can be done through some heuristics. In the game of Go, this was really one of the main difficulties. So this is how you then take these two train elements and you create a policy improvement operator that is using a model of the environment. In this case, the model is really the true environment. This environment is very simple. Your action is move here and then a stone appears here, or move here, the stone appears here. But we'll see later how this is expanded to more environments where the transition function is not basically trivial. Although in Go, of course, when there are captures of stones, some non-trivial things happen that you need to know the rules quite carefully. So hopefully you see what like the first AlphaGo works and the main intuitions. Let me go, before we open for questions for the whole AlphaGo / AlphaZero story. Let me just tell you a bit how AlphaGo 0 was changed. The change was mostly in the methodology. The actual search procedure is identical. So there was this slightly annoying element in AlphaGo, which was we require human knowledge to play the game, to leverage from human trajectories to understand the game of Go. And also, it was a bit clunky to have these 2 stages of training and so on. So AlphaZero really changed the name of the game by essentially creating a single algorithm that was able to create superhuman player of Go. And it changed only the way in which you get the labels for the policy and the value. It did not change the basics that I just explained in terms of using a policy and a value to then change a version of tree search, which is called Monte Carlo tree search, to improve over what the policy alone would be able to do, right? So the key element here is that you have a policy that's okay, and if you have a value that's also okay, thanks to the tree search, you're going to get a much stronger action out of this, which is precisely the first slide in model-based reinforcement learning that I showed. So in a nutshell, the way it worked is like, okay, look, let's not pre-train neither the policy or the value. Let's train them online, on the fly, all the time. And to do that, we're going to start literally from an untrained neural network for the policy and the value. So this is a very, very bad player of the game of Go. Then you use tree search to find a move that you're going to play from the position. So you have your untrained policy, you get a move, and then given this move, you do it again, and so on and so forth, until you finish the full game of Go, which will not look really great from random networks, of course. These are very bad players. But actually, MCTS helps you a bit already, because MCTS alone actually was a state-of-the-art Go player at the time. So it's a very nice inductive bias for this kind of game. And then you finish your game, you see who wins, which side wins. And what you're going to do after finishing the game is trying to essentially do 2 things. First, as you finish the game and as in AlphaGo, you're going to improve your value network to say, okay, the value throughout the game will try to predict that, in this case, let's say white wins, right? So that is how you get the labels for the value, very similar to AlphaGo. But crucially, the policy now is just going to be distilled from the better moves that you got from the running MCTS search, right? So the policy maybe had a very bad move, but then thanks to search, this move was largely improved. You got a much better move out of this every position you've seen in that particular game. So you're going to treat the actual moves you played, which are an improved version of the moves that the policy would have played. You use that as supervision. You literally distill with the distillation from the better move onto the policy. So now the policy, the neural network that's trying to predict the move from the get-go, hopefully has improved. And then you keep repeating this process over and over and over, right? So the policy improves, the value improves, then you play another game, the game looks better, and then you again distill that better moves and the better value prediction onto the neural networks. You keep doing this over and over and over, and eventually you get, so you repeat this process as many times as you can, and then you get these kind of amazing training curves that from scratch, from an extremely bad play of Go, you surpass first the Lee Sedol version that was the AlphaGo version that you can go and rewatch from March 2016. And it also wins against an improved version thanks to tuning the neural network and so on that was used later on for, I believe, in the Nature paper. And these actually surpasses both from scratch without any sort of human prior. So that really was kind of, and this depicts that this happens through kind of days of running this process, right? So sample efficiency here is a challenge. But after 40 days, you get a very strong player of Go. And in this case, with a very elegant algorithm that uses only self-play and this idea that search is a very good policy improvement operator for the game of Go. So at this point, let me add this line here to unpack a bit what kind of model-based reinforcement learning, MCTS or AlphaGo is. And then we can do a few questions if you have some thoughts on the whole story of AlphaGo behind AlphaGo. So maybe the main difference between these and other methods that I was describing before is that in AlphaGo, you can only apply this kind of method in deterministic environments, right? So Go, chess, these are games where you play a move and then the next state is fully determined by a game engine that is deterministic. This is a limitation of this algorithm, as we'll see very, very soon, that prevented us from attempting this in the game of StarCraft for obvious reasons that will become apparent in a few minutes. Now, in inference, the way you improve the policy is not through backpropagating some function of state through the actions, but actually, as you saw, through searching as deep and as wide as you can, given some compute budget. And this improves the actions quite a bit. And what, as I said, Rich Sutton motivated his sort of the bitter lesson